4 compounds of comparable molecular mass are used to investigate the effect of functional groups on vapor pressure. The results obtained are shown in the table below. We are given the compounds and then their corresponding vapor pressure. 4.1. Define the term functional group of an organic compound. So this refers to the group of atoms that are responsible for the physical and chemical properties of a group of compounds. 4.2. Which one of the compounds in the table has the highest boiling point? Refer to the vapor pressures in the table to give a reason for the answer. Okay, so the compound that has the lowest vapor pressure, it is the one that is going to have the highest boiling point. So in this instance, we have D. D has the lowest vapor pressure, so it will have the highest boiling point. So it has the lowest vapor pressure. Okay. 4.2.2. The weakest intermolecular forces. Alkanes have the lowest, the weakest intermolecular forces, so it is going to be A. 4.3. Refer to the type of intermolecular forces to explain the difference between the vapor pressures of compound A and B. We have A and B. We have butane there, so it's 1, 2, 3, 4. Okay. Whenever you have carbons and hydrogens only, this means that you're going to have what? The London dispersion forces, or these are called the weak van der Waals forces. Okay, so for B we have propan 2O, 2, 3. Okay, so we know that oxygen is highly electronegative, and then this means that it likes to acquire electrons, or it pulls electrons towards its nucleus. So this is going to acquire a partially negative charge, and then the carbon is going to have a partially positive charge. And then we are saying that oxygen will pull electrons towards its nucleus. So we'll have a dipole moment in that direction. So it means that the type of forces that we have here, it is the London forces, the London dispersion, and then we also have what? An induced, or we can just say the dipole forces, right? And then we're going to explain. So the dipole forces are stronger than what? The London dispersion. So we need more energy to separate the molecules of compound B. So we will say more energy is required to separate the molecules of compound B. Thus, B has a lower vapor pressure. Okay, maybe we can try and use a different method to explain. So imagine that we have two containers. So these containers, they are exactly the same, and then they are sealable. And then we put equal volumes of A and B. So this is A and that is B. Okay, and then let's just say we run this experiment for 1 minute. We are saying that the intermolecular forces of A, which is the London dispersions, they are easy to break, right? So if these two are placed on a stove and then we turn the stove on, A is going to boil much faster. So it means that we will have more gas formed there. And if we have more gas, it means that the gas will exert more pressure on the walls of the container compared to B, which is going to reach its boiling point far later on. So it means that we have a higher vapor pressure for A because of more gaseous atoms, more gaseous molecules being formed, right? So they will exert more pressure on the walls of the container, which makes sense. So it means that when you have a low boiling point, you will have a high vapor pressure, and vice versa. Okay. 4.4. The vapor pressures of compounds C and D are much lower than those of compounds A and B. Name the type of intermolecular force, in A and B that is responsible for this difference. Well, C is an alcohol and then D is a carboxylic acid. Alcohols and carboxylic acid have hydrogen bonding. So they have hydrogen bonds. Hydrogen bonds. Then 4.5, so this is C and D. Briefly explain the difference in vapor pressure between compound C and compound D. Okay. So we have an alcohol and then we also have a carboxylic acid. When you look at the alcohol, you only have what? One hydrogen bond. So you have one site that is possible for hydrogen bonding, right? For the carboxylic acids, you can have this pi bond breaking and then forming electrons there. So you will have something like this. And then you have an OH there. So this oxygen, now it is negative. So it can attract what? A hydrogen atom. And then you can have what? Hydrogen bonding there. You can also have hydrogen bonding there. So it means that for D, you have two possible sites for hydrogen bonding, while for C, you only have one, which is why D has what? Has the lowest vapor pressure. So it means that it has the highest what? The highest boiling point. Okay, so we will say for D, there's two sites possible for hydrogen bonding. Therefore, it will have the lowest vapor pressure than C. Okay. 4.6. 6. During a combustion reaction in an enclosed container of adjustable volume, 8 cubic centimeters of compound A reacts in excess oxygen according to the following balanced equation. So we have a combustion of an alkane. It is a complete combustion because the oxygen is in excess. And then we are forming 8 carbon dioxide plus 10 water. We are told that the volume for the alkane is 8 cubic centimeters. Okay. If the initial volume of the oxygen in the container was 60, the volume there is 60 cubic centimeters, calculate the total volume of the gases that are present in the container at the end of the reaction. All the gases in the container are at the same temperature and pressure. Okay, so the first part we are told that the oxygen is in excess. So this means that butane is the limiting reactant. So this means that as soon as the butane is depleted, the reaction is going to stop. Okay. So the first thing to do here is to find out how much of the oxygen is needed in order to react completely with what? With the butane. So we will use the balancing numbers. We have C4H10, and then we have oxygen there. And then we have a 2, and then we have 13 this side. We know that this 8 is going, the volume of the butane is going to react completely with a certain volume of the oxygen. We want to know what that volume is. Right. And then 8 times 13 divided by 2. So I am getting 52 cubic centimeters. So it means that I need 52 cubic centimeters of the oxygen in order to deplete the butane. So the oxygen that is left is going to be equals to the 60 minus the 52. So I have 8 cubic centimeters of the oxygen left inside the container. Okay. Now I need to find out how much of the product I have formed. Same thing, I am going to use the limiting reactant in order to find how much product I have formed. So we have C4H10, then carbon dioxide, and then C4H10, and then I have water there. So this is 2, and that's 8. This is 2, and that's 10. Okay. And then I know that here I have 8. I just need to know how much of the carbon dioxide is formed. Okay. 8 times 8, that is 64, divided by 2, that's 32 cm cubed of the carbon dioxide. And then 8, so it is 40. So I am going to form 32 cubic centimeters of carbon dioxide and 40 cubic centimeters of the water. Now it means that the total volume of the gas, it is going to be the oxygen that is left, which is 8, plus the 32 of the carbon dioxide, plus the 40. So this is going to be 80 cubic centimeters.